measured surface tension of these solutions of potassium chloride. And you see it's a nice straight line. Just like Horvath said it would be, it's proportional to the surface tension of the water of the aqueous phase. As you add these salts to water, you raise the surface tension of the water. As you add organic to water, you lower the surface tension, and therefore you lower retention. So it's a nice story. If we plot log K versus the surface tension, here's cinnamic acid, here's benzoic acid, there's methanol, there's acetonitrile. You can see that they sort of both follow the surface tension curves. They're not exactly straight, but as you're adding these solvents to water, you're changing the dielectric constant of the water, you're changing dipole-induced dipole interactions, and so on and so forth. So I don't think it's fair to say the model doesn't work, because this is not a straight line versus that surface tension. There's too much going on. You're modifying too many of the electrostatic free energies, and not just the cavity term. So Horvath's basic conclusions are that the solvent-phobic hydrophobic theory of reverse phase chromatography is right. This means that the free energy of retention of the nonpolar parts of the analyte are driven by the unfavorable entropy of solution in water. And he's saying hydrophobic effect, dead on, no problem. Forget about lipophilicity, doesn't matter. He's agreeing with Tanford, he's agreeing with Breslau, he's agreeing with the received wisdom at that point in time. Let's do a thermodynamic analysis of the problem. This is what we mean by reverse phase chromatography, where this is polar and this is nonpolar, polar, nonpolar. We can break down this simple direct transfer from the mobile phase to the stationary phase into two simpler steps. We can ask what's the free energy, how favorable is this process, and how favorable is that process, and we can add them up appropriately, and we can see where the energy is coming from. Because in the gas phase, at normal pressures, normal temperatures, the molecules don't interact with one another. So if I can measure this free energy, it's telling me essentially how the solute molecule is interacting with that stuff. And if I can measure this free energy, it's telling me how the solute molecules are interacting with that stuff, because this is essentially ideal. And there aren't interactions in ideal gases. Well, you can do this. We can measure this process simply by doing real reverse phase chromatography. And it's been done to death. Here's a whole bunch of data in 90% methanol, 10% water into C18 phases for a series of phenylalkanes, alkanes, alkyl chlorides, methyl esters of carboxylic acids, alcohols, and N-alkanones. And you can see that log K prime is linear with the number of CH2 groups in the molecule. And they're nice straight lines. This is the Martin equation for reverse phase chromatography. And the slopes of these lines are really very, very parallel. It's kind of amazingly good. And that was a very nice study by Chopla and George Duchamp in the early 80s. But we can measure this gas phase to stationary phase free energy if we make an approximation. And the approximation is that we're going to use bulk liquid hexadecane as a model of the reversed stationary phase. And there's lots and lots of data hanging around in the GC literature and in the chemical engineering literature, and you can measure some of this stuff not very well without doing some kind of chromatography, but you can. And you can measure the logarithm of what we call the L16, which is the gas to C16 partition coefficient, for a whole bunch of compounds, just like Guillaume and Chapala did for reverse phase chromatography. And they're nice straight lines, and this is the Martin equation for gas chromatography into hexadecane. And they're nice straight lines, and the slopes maybe aren't quite as parallel as we saw a minute ago, but let's not get picky about it. And you can see, either in this case or in this case, the transfer free energy of a CH2 group, which is the slope of the line, right, is the slope of the line, is becoming more favorable as we move up the homolog series. So the free energy of transfer of a CH2 group, either in reverse phase or in gas to hexadecane, is a favorable process. This is a little tougher measurement. This is the measurement of the gas phase to mobile phase using water as the mobile phase. So we now have, if we can get this, we got two legs of that triangle, and we can compare that result to the direct reverse phase process. We see here that for all of these homolog series, alcohols, ketones, nitriles, nitros, formates, acetates, isoacetates, and aldehydes, all the equilibrium constants for transfer into water are becoming less favorable. They should be. The more nonpolar the molecule is, the less soluble it's going to be in water. So the smaller the partition coefficient into water out of the gas phase is going to be. So now we have this and we have this. Here's the water data. And here's the data. This is for the solutes are the N-alkanes, starting at N-pentane. Then so we got N-pentane, hexane, heptane, octane, nonane. And these are the organic solvent that they're going into, with hexadecane being this solvent down here. You see that in all cases where it's an organic, it's gas to organic, the process is becoming more favorable. The delta G is going negative, favorable. In the case of water, it's going up, it's becoming less favorable. But let me point out that all of these slopes are larger in magnitude than that slope. There's actually two data sets here. One is water, one is D2O. There's no difference between water and D2O. The solutes here are methanol, ethanol, propanol, butanol, and pentanol. And we're normalizing to the transfer from methanol. So the alcohols become less soluble in water as you go up the chain, and they become more soluble in all the organics, including hexadecane, as you go up the chain. Same result as we saw for the N-alkane solutes. So we have this and we have this, and we can measure this for reverse phase chromatography using a real reverse phase. And we can do this for a whole bunch of homolog series running from alkanes to alcohols. Here's the energy of the CH2 group interacting with the gas phase. 0. Here's the free energy of transferring a CH2 group from gas phase to water. Here's the free energy of transferring a CH2 group from gas phase into hexadecane. That's this distance. What's the free energy of transfer from water into hexadecane? That's the distance from here down to there. Which part is bigger? This is not a hard question. Regardless of the homolog series, the transfer from gas into the hexadecane far and away outweighs the transfer from gas into water. The water does make a favorable contribution to the transfer from water to the hexadecane. It's that big for this homolog series. It's that big for that homolog series. But surely, this process of transfer from here to here is not driven by the stuff wanting to get out of the water. It's really driven by its wanting to get into the nonpolar environment. This is just bookkeeping. There's not a model. Now this is bulk water to bulk hexadecane. We can do the same experiment of water methanol into hexadecane. And we can do that as we vary the amount of methanol. Here's pure water. This is 10% methanol, 90% water. This is 100% methanol. This is gas phase. There's the water to gas phase contribution. Here's the gas phase to hexadecane contribution. As we add methanol to the water, this moves down, down, down. It crosses over somewhere between 20 and 30%. And we wind up at 100% methanol. This is the contribution from gas to methanol, and this is the contribution from gas to hexadecane, and there's the reverse phase process. It's gotten a lot less favorable. The transfer from the mobile phase to the stationary phase becomes less favorable as we add organic solvent to the water. But we can see that up until a fairly large amount of methanol has been added, the dominant process is the attraction of the CH2 group for the hexadecane, not its desire to get out of water or water methanol. Again, just bookkeeping. So the free energy gained by a CH2 group leaving water is rather smaller than the free energy of CH2 than a CH2 gains by going into the less polar solvent. Thus, reverse phase processes like protein structure, etc., 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 are not hydrophobically driven. They are lipophilically driven. The London dispersion interaction is the dominant force. McBain and Debye were right. 60 years ago. Yes, 70 years ago. So that's one question. It is a lipophilically driven process. It's not hydrophobically driven. Now let's look at the other question of partition versus adsorption. And we're going to answer that one by looking at the ratio of the free energy of transfer of a CH2 group from mobile phase to bulk hexadecane. That must be a partitioning process. We can do this with a very teeny tiny surface area between the two liquid phases. It's not an interfacial adsorption process. It's a bulk transfer process. And compare that bulk free energy to the free energy measured in a real reverse phase system at the same mobile phase composition. So we're going to take that ratio. And according to the Dorsey-Dill cubic lattice model, which is a very crude model, if the reverse phase process in the real reverse phase is the same as the bulk process, the ratio of free energy is going to be close to 1. But if it's an adsorption process, the bulk free energy relative to the reverse phase process is going to be about 6 times bigger. So here's that ratio, F. Here's percent methanol. This is with a C3, a propyl silane phase. This is with a methyl silane phase. This takes us almost up to 90% methanol. Ratio is only 2. If we look at C18, that ratio is about 1.2. With a long chain alkane bonded to the surface, the free energy ratio is pretty close. It's definitely not 1. It's a little higher than 1 relative to the bulk phase process. That is easily argued away by saying that when you glue something to a surface, you're going to change the number of configurations that that molecule can have, as opposed to when it's allowed to swim around at will in a bulk liquid. Clearly, for the long chain silanes, this is much closer to a partitioning process than an adsorption process, which means that the CH2 groups, the non-polar parts of the molecule, are really down here. And there are not much of them out here at the interface between the two phases. This would be the adsorption, this would be the partition or embedded situation. The statistical mechanical models, the dynamic models of Zietman and Schur certainly emphasize the fact that the solute is more nearly in this type of state than in this type of state, although occasionally at equilibrium you definitely see a solute molecule hanging around the interface between the two. But the ratio of these is dominantly in favor of the embedding model. So, the conclusions: the free energy of retention of the CH3 group is predominantly driven by lipophilic attractions, not hydrophobic repulsion. The nonpolar parts of the solute are embedded within the bonded alkyl chains, and partition is dominant. Does this mean that every molecule partitions and none adsorbs? No, because if you have a really polar molecule, something like phenol, benzyl alcohol, benzoic acid, it's going to want to stick those polar functional groups up towards the methanol water. So they're more likely to undergo a more adsorption-like process than are the nonpolar parts of the molecule. But they are in one molecule. You can't get the polar part too far away from the non-polar part. You're not going to break any carbon-carbon bonds to make it really happy. That's just giving up too much energy. But non-polar molecules are clearly embedded. Okay, went over a little bit. Let's take a 5-minute break and hit normal phase. We can come back and do questions on this in a bit.